last time we did the t-score stuff. Section 8.2 is exactly like section 8.1, except in 8.2 we're using t-scores for the most part. 8.1 we're not. And it's completely, so what needs to be true in order to use a z-score? What needs to be true in order to use a z-score to make a confidence interval? We know one thing for damn sure, right? We have multiple ways to check this truth. I can't use the table unless this is true. What do we want to be working with in statistics? And I can use the thing with all the answers on it. Normal. Okay, so we have n greater than 30 for means. We have NP, NQ greater than equal to 5 for percentages. We have all these tests. Why is it so important to know if it's normal? Because then I know all the probabilities. I know exactly where they are. I know exactly how far away things are. I can be very specific. If I don't know it's normal, oh shit, right? That would be stats 2 if we offered stats 2 here, which we don't. So z-score, one requirement is normal, right? So either they say it's normal, or n greater than 30 for means, or NP and NQ at least 5 for percentages. Okay, right? You guys with me? So all of those are just all different ways to find out if the damn thing is normal. So if it's not normal, it doesn't matter which standard deviation I know, I can't do anything. I just kind of gave away the second requirement. Once I know it's normal, what do I look to distinguish between Z and T? You just told me this earlier. When can I use the Z-score? When I know what? When I know sigma, when I know the population. So population standard deviation must be known. So if these two things are true, we can use a z-score. For t-score, this whole first thing is the same. Still has to be normal. But of course, sigma unknown. Only S known. What's S? Sample standard deviation, kick ass, right? So when I calculate a sample standard deviation, that is my best guess for the actual population standard deviation. Yes? That's why we just throw it in place of sigma, we throw an S in when that's all we know. But when we're making confidence intervals, we have to kind of cover our ass for that unknown thing. So t-scores make our intervals a little bit wider, just to cover our ass for that unknown piece. I like it. Okay. There's no specific questions from chapter 8. Yes.
I have a couple of questions. I think this is the questions that I have were to be specific to what the book was asking about on the homework.
There's this.
There's the notation key, and then it has a little apostrophe.
Oh crap! I keep forgetting. So my p hat, the book uses p prime.
So that's the same thing.
Same thing.
I figured, but I was like.
I always forget that this book. It's the only book I've ever seen that uses this. So, yeah. So weird. It's really weird to me because this symbol means something entirely different in calculus.
Yeah.
Yeah. So I'm going to use p hat. The book likes to use this. It's called p prime.
Okay.
Yeah.
Another question a lot of the questions in the book are like, state which distribution
Yes.
you would use. So
Yes.
you would use that thing that's like p prime or whatever. And then the
Well, really, the main thing there is it a z distribution or a t distribution?
Okay.
Yeah. I mean, in this, with confidence intervals, that's the main distinction. We know it's normal. It has to be normal to do anything. But, so the real distinction then is it a z distribution or is it a t distribution?
Okay. I guess just like the book is like some specific things that are like.
Yeah, there's a whole little section where they ask you what distribution, and sometimes the answer is actually binomial. It depends on the situation they give you. Yep. Anything else? No? Okay, so anytime, you gotta help me out, because I will sometimes forget this book. That's one little thing I always forget, that it doesn't use a hat, because every other book I know uses a little hat, dude. And I guess if it's a free book, this little symbol costs more to make. I'm joking. I don't. So I have no idea why they don't use it here, but they just don't. If there's anything else in the book that's weird, the way they ask something or what they use, just let me know. Yeah. Normally it's just a different choice of notation.
Everything is the same, except it just, I was like, I know in theory that it has to be asking about PHAT, but it's not PHAT.
I got you. Okay. So now we know if you see this in the book, they mean this.
But in the quiz, you want us to use
This, yeah. Okay. Anything else before we're gonna actually get into chapter 9 if there is no questions? Do you all feel comfortable with the T chart now? I should add that. Anybody feel uncomfortable with the T-score chart? No, okay. All right. Does anyone want to do an example? Okay, all right, I love you guys.
Yes.
Yeah, that's great.
Okay, so you all understand, am I really difficult to request things from? Am I not picking up on myself? You guys can always, this is why I'm asking you. You have a question, and your question could be, could you do an example of these crazy things? Like, sure. All right, let's say we get a new marker. Let's say that we, one of you guys has got to be good. Yeah. We sample 71 people and find X bar equal to, you can do it, Jeff. 41.2, let's make it their ages. Years with standard deviation of 7.12 years. Okay. Now, some of the homework will give you like a list of data, so you have to put it into your one more stats. Right? So that's why I did an example like that last time. One more stats, you can get your X bar, you can get your S. Yes? You guys okay? So they're not always going to just give it to you. Find the 90% confidence interval, or the true mean age. People, wherever this is. Okay. So the first question is, how do we know we can do something? And what is it we're gonna do? Exactly. So what do we need to distinguish between, right? So we have, how many confidence interval formulas do we have? All right. We have confidence intervals for means, right? And we have confidence intervals for percentages, yes? And the means one has a z option and a t option. So how many confidence interval formulas do we have? 3, right? We have an x bar with a z, we got an x bar with a t, and then we have p hat stuff, right? Okay. Quick little thing, I don't know if you guys, so again, we got this guy, we got this guy, and then we got this guy. And the only other ones we have, are the formulas that solve for n, right? If they ask you how large of a sample do you need. All right. So the thing that students always hate is Jeff doesn't let them freaking write notes. Right? You let us write the formulas, but you don't let us write notes. But the formulas are freaking notes. When do I use a t-score? When I know S. When I use a z-score? When I know sigma. Right? So it's right there. It's right there. You know exactly. And I have to let you write the formulas down. So it's a note. Now notice this, how many options is there for percentages? How many options are there for percentages? 1. And does it have it's got a z in it, so do I ever use t-scores? No, it doesn't have that option. T-scores were invented for x bar stuff. It was invented for s and all that kind of stuff. With percentages, we create our own standard deviation. So we're golden there. We can use the z-score as long as NP and NQ are bigger than or equal to 5, right? Okay, now, I know I'm not going to use this one, correct? I can eliminate that one because this is all means, not percentages. How do I know between these two options which one I'm going to do? What do I check? How do I know I can do something? Oh, okay, there's an S. That doesn't tell me I can do something. It does tell me which thing I can do. What tells me I can do something, that this is not impossible for me? What has to be true?
It's normal.
Why? How do you know it's normal?
More than 30, 71.
It's normal, so that means I could do something. Now, you said we know the S. What does that mean we're going to use? T-score, I love it. So we got to use a t-score for this. I like it. Okay. So we know x bar. So we're not going to use this one. We use this one. We know x bar. We know s. We know n. We just have to find our t-scores. You guys have your t-score charts? Do I have my t-score chart? Yes. What do I have to know to be able to look at the t-score chart correctly? I have to know my... Okay, alpha. Okay. What's alpha? 10%, right? So 0.10 and 2 tails, right? 0.10. So now I know which column to look in, yes? How do I know where to stop? Yeah, degrees of freedom, right? What's my degrees of freedom? 71 minus 1. So if you look in the 0.10 column, which column is that? 0.10 and 2 tails, right? Because it's outside total, 2 tails 10. So there looks to be the 4th column over, yes? And then you go stop at 70. What do you guys get? .667. I like it. Now, does somebody have their z-score chart handy? Do you remember the little, we'll call it the tiny chart? Yes? The tiny chart in the corner. What z-score would we have used if we were allowed to use a z-score for a 90% confidence interval? 0.90 confidence level, what z-score would we have used? 1645. So that's a little bit bigger, yes? That's the whole point of a t-score, is to cover our ass a little more because there's an element that we're not sure about. We're using S to estimate. We don't know what the hell sigma is. We better cover our ass a little bit for that. So that's the main job of the t-score. Just make it, we can go out a little bit further. Okay, maybe. So now I got everything I need. So now it's a plug and shove situation. So I got my x bar plus minus ts over square root of n. X bar 41.2, give or take 1.667 times 7.12 divided by square root of 71.
Quick question.
Yes.
Why did we do area in 2 tells instead of area in 1 tell?
You can do either one. So if you have a 90, look, if you have a 90% confidence interval, how much total is outside?
10%.
So that's in 2 tails. So how much is in 1 tail?
And
Isn't that cool? Aren't you in the same column then?
yeah.
So no matter which way you cut it up, you should stay in the same column. Yeah.
Okay, I see what you're saying.
And like I said, the next chapter, we're really going to see why we have a 1 and a 2 tail option. It's going to make a lot more sense. Yeah.
Is the next chapter, well, is there anything like, are we going over, say like, we have a confidence interval, but there's like 4% on this side and 6% on this side?
Oh,
Or is that like?
that's not going to happen with normal or t distributions because they're both symmetric.
Okay.
There is a distribution later that is not symmetric, so then it's not going to be even, the intervals. Yeah. But since these are symmetric, they're always going to be equal both sides. Yeah. So then what would you do to figure this out? You would, first, I would highly recommend you figure out what the error is first. 0.8. I don't know, I get 1, I'm way off, I'm sure, 1.3 in my head.
Well, 1.41.
What is it? 1.41? Hey, not too bad. All right. 1.41. Okay, I like it. So then you just do 41.2 minus 1.41. Oh, what the hell is that? Is it that? And 41.2 plus 1.41. Is that right? Yep. Okay. So this confidence intervals to me, the concept is not too weird, I hope. We have a mean, and then if I just kind of go down and up, I'm going to catch so much. So of course I'm that confident that I caught something specific. And what is that something specific in this case? The population mean, right? So I'm that confident I caught it. How do I write my conclusion?
We are 90% confident that the intervals 39.79 years to 42.61 years are the.
So one thing is just one interval, right?
Yes.
One interval has 2 sides. And it can't equal something because it's a whole range of stuff. So what is it? I want my interval to do what to the mean? The mean is out there, and I'm going to throw a net, and I'm hoping I'm going to catch it. So you can either say catches or contains
Okay.
the true mean age of people in the area where I am. True of, I love it, Chuck. The true mean age of people, blah, blah, wherever the hell. Okay. I wasn't that specific in this problem I just made up. Yes?
I could put true mean age of population.
Sure.
Right.
Well, Well, yeah, okay, so you can either say, so I say the word true, and I'm just not gonna let go of it, because I've done that forever, because my teacher said true, but it really technically should say it contains the population mean age of people. So you have to go back to what the situation is. Right, so this could be of people in a certain housing program, right? You have to say that in your conclusion. Yeah. Okay.
So you could say the population of,
People in whatever place. I wasn't that specific in this one, so yeah. Is that all right? I mean, that's exactly how all three sections in Chapter 8 work. Just one uses z-scores with means, the other one uses t-scores with means, and the other one has the p-hat business. Right?
should we do the p-hat, like just
Yeah.
an example?
Is everybody cool with this? And all that? Okay.
And then what we did is all stuff from like 8.2, right?
That was 8.2, yeah. 8.2 is t-score stuff. This is going to be 8.3. 112 out of 407 people sampled said that they like turnips. Does anyone like turnips? Has anyone ever had a turnip?
I'm not opposed to turnips.
Not opposed, okay, I see.
So what's the term we did?
Turnip is a vegetable. That's
Oh,
about
yeah.
all I did, to be honest.
I was thinking like the push pop or like that.
Oh, I see what you mean. Turn it, twist it, no. Okay. Find the, let's do 98% confidence interval for the population percentage that like terms. Now that seems a lot less wordy than the other one, right? I don't have to give you as much information. So what's the very first thing we need to do? Am I allowed to do anything? Am I allowed to do this problem?
Yes.
Why? What do I check?
You have a sample of 407 people, which is, now you have to check n times p. and then-
N times p hat? N times q hat? So I don't know if you guys, well, let's see. So what is p hat? How do you calculate it? What do you see in the sample? How many out of how many said something?
0.275.
Where do you get that from?
112.
Yeah, 112 out of 407 people, so. I know this is a percentage also, but what's this guy's only job? What's the only job this guy has? What am I gonna get from this guy?
Z-score.
Z-score, that's all he's there for, right? It's the only reason he's there. So don't be bringing that into p-hat shit. That's gotta be what I see in my sample, is what p-hat is. And what, I'm sorry, you said it was 0.275?
Yeah.
I'll go with that until somebody tells me otherwise. So what's q-hat?
.725.
Yep. So somebody help me out. Look how easy this is. N times p hat would be 407 times 0.275. What is 407 times 0.275? 112. You guys see that? 6 divided by 3 is 2, so 2 times 3 is 6. P hat times n is 112.
How did you get, Q hat?
Say again?
How did you get?
Oh, what's always true about P and Q, no matter what clothes they're wearing? They have to add to be 1.
Oh, okay, so you just did 1 minus 2 point, okay.
Yep.
Or point-
That's what Knight did, I think, he's the one told. And so what's NQ hat? Here's the other, so if you wanted to, you could just do 407 times 0.275. It's not gonna be 112 exactly because we rounded, didn't we? NQ hat, you could do the same thing, or you could just say there's 407 people total, 112 are there, so the rest are gonna be here. So that's gonna be 295, I think. And again, if you don't know what I'm talking about, just do 407 times 0.725. Just do N times Q hat, and you'll get roughly this. What's true, what's the big deal with these? Why is this good?
They're over 5.
Yeah, they're at least 5. Check! So it means the same thing as N greater than 30 for means. It means the exact same thing. It's normal enough to do something.
What if it's not above 5?
Then you don't do it.
Oh.
Now, to be honest, I think in the homework there's one problem where it's like that, but you should say, technically we shouldn't, but then you do it, right? Just because you need the practice. But and on a test or something, you should do it because there could be something you're missing, or you could have made a mistake. I try not to do that. I try not to make a problem where you would waste a bunch of time doing it just because you didn't notice something. That would be evil. Okay. So since this is normal, that means I can use the formula that's been crossed out from earlier, but oh well. And now I just plug and chug. So I just put in there, let's see, 0.275. Give or take. Oh, did we look up the z-score yet? No. Can somebody look that up for me? With 98%, what's alpha? It's 98%. How much is outside? 102. And that's in 2 tails, of course, right? So what do you guys get? Are you using your t-score chart like you should be? Is anyone concerned that this is supposed to be a z-score? Why are we using a t-score chart? Where are z-scores? Where are they on the t-score chart? At the very bottom, right? So if you look in the 0.02 in the second column, right? And you go all the way to the bottom, what do you get? 2.326. And then you've got p hat, q hat, over n, of course. All right, so it's plug and chug, yes.
So, how do we get the z-score from the t-score chart if the percentage is like 97%?
Can't, so then you have to use the z-score chart, so do it the old-fashioned.
So
So if I wanted you to do a 97% confidence interval, that means there's 0.015 out here, you would find 0.05, 0.15, and you look and see, yeah.
So we're gonna be using both charts?
Yes.
Okay.
Damn sure. I like it.
So it's- what he was asking was if you can't find it on the t-score, then you go to the z-score?
Then you have to do it the old-fashioned way, where you look at what's in the one tail, and you find it in the body, and you look out to see what the z-score is. Remember, that's the way we used to have to do it, and then I pointed out the little tiny corner chart, and then we got the t-score chart for the ultimate shortcut. Okay. Now we just gotta throw this in the calculator. I don't know what that is. It's like 0.05, 0.047.
Very close.
What is it?
About 0.049. no, I calculated numbers wrong, my bad.
I got 0.051, that's still pretty good. It's not bad. 275 plus or minus 0.0515. I like it. You guys agree? Is that what you guys got? Anybody else? And now you just gotta add it, subtract it. Right, so we start with our guess, and we improve on our guess by going up and down, so then we can report that interval to people. And it communicates a lot of stuff to somebody. It tells them how certain I am about what we found and so forth. So this would be oh god. I want to be 2235 up to 3265, I think. Maybe. Yeah. Okay. So write the conclusion real quick, and then I'll
Quick
do it.
question.
Yes.
When you're doing the decimal place, how many decimal places do you usually want it?
So this one's gonna be one more place than this.
Okay.
Yeah, and then this, it's okay if you round after that, for whatever reason, I just didn't. Yep. Yep.
Is there any homework problems or, test questions where it's 100% CI?
All right, I really want you to think about this. Theoretically, to be 100% confident, what happens out here? We haven't really talked about it. What happens out here? Does this ever get to the x-axis? No. So where would you have to go to be 100% confident? I think I said this once. You would say, I'm 100% confident that the average age people at Grossmont is from negative infinity to infinity. That's the only damn way to be 100% confident. Well, let me say this again. If they give me the population data, I'm 100% confident about the population. But if I get a sample, the only way to be 100% confident is negative infinity. Okay, I like it. And then, all right, so let's see. We are 98% confident that the interval 0.35% to 32.65% contains the true percent of people who like terms. Woo! All right. Whew. Okay. Oh man, blue does not.
Is there ever like a given when you can tell when you're gonna want to use like the p-hat formula over like the sample mean formula?
Oh, I mean, it's gonna be really clear if you are working with means or if you're working with percentages. In fact, you're gonna have to say, find the whatever percent confidence interval for the true percentage, percentages of percent, or for the true mean. That's a giveaway, right? Then you can immediately cross at least one equation out for that problem, right? Okay. All right, now.
Excuse me?
Yeah.
So, just for when we use the t-score instead of the z-score, it's only, if the tail's outside, the values fall within the numbers above here, right?
Say it one more time.
So when do we use the t-score and z-score for this problem again?
All right. What is the one thing that determines between T and Z? That's what you're asking, right?
Yes.
Okay, who knows? What's the one thing that will tell me which thing to use, T or Z?
S.
Yes? Yes? Yes. What about that? Keep going. If I only know S and I don't know sigma, what do I use?
The T-score.
T-score. Okay, so T-scores were invented for when we only know S. Period. End of statement. Right? So the very first thing I should know is, can I do anything? So that's just seeing if it's normal, right? And then, if it's a means problem, I gotta go, which standard deviation do I know? Right? So what I always get is people say, I can use Z-scores because I know the standard deviation. Like, that doesn't make any damn sense. Which standard deviation do you know? Right? Okay. I like it. Oh, you suck, yeah. Yeah, you're better. Okay, so we are now getting into the real process we use to evaluate a claim. So confidence intervals sort of go in that direction. For example, if somebody claimed the mean is 11 and we create a confidence interval like this, is that evidence their claim is false? What does their confidence interval say it looks like catches the mean? Somewhere from,
Oh, yes, wouldn't that be false?
that's evidence, it's not proof. Because this is it's definitely less than 100% confident because it doesn't go to infinities, right? So if this is like 95% confident, that's pretty good evidence that it's less than 11. Yes? Okay, I like it. Can we ever get proof in this method? Shit, no. Because we have to always rely on samples. And samples could fluctuate wildly. Yes? That's why if a study comes out and they see something, they're not going to be trusted until it's at least replicated a few times somewhere else, right? If somebody else does the exact same study and it's like the other side of things, you're like, what? That was just a fluke. That's why you need to repeat the findings at least once, if not multiple times. Then you go, oh shit, that looks real. You guys semi with me? Yes? All right. But confidence intervals are not really built to do that. You could sort of use them that way, but we need something more specific. And the real problem with confidence intervals is, what are they built off of? What do I use to build from? I use the sample mean or the sample percentage. And couldn't those be kind of off by quite a bit? Yes? You with me? Okay. So they have a kind of a fundamental flaw. So they're not meant to be how I test claims. That's not really their purpose. Their purpose is just to communicate better how certain we are about what we see. Right? So like that one example we did where the grade was anywhere from 59 to 96, is that a good thing to report? No. But what if the average grade was anywhere from an 82 to an 85? Do you feel better reporting those findings? Shit, yeah, right? So it does have a purpose. It does communicate how certain we are about what we see, right? Okay, so the thing that we actually built to test claims, and claims we're going to call hypotheses. So hypothesis test. Oh shit. You're gonna love this. When I learned this, there were 8 steps that I was taught to this process. 8 steps for every problem, right? I have cut it down to 5 for you, right? And you're still gonna balk about 5, but oh well, too bad. Just imagine it could have been 8 steps. Now there's 5. So let's talk about the idea behind this. So let's say, I'm not going to come up with a better example, am I? Oh, creativity, waiting. Okay. I keep going back to this, but let's say that I have a program that you can go through that will improve SAT scores. Right? That's my claim. So my claim is that my program will improve SAT scores. How, you guys just tell me, how would you test that claim? What would you do? If you wanted to test that claim,
Take the SAT. and
Say again?
Make a bunch of people take your program. Take the SAT and see.
yeah, doesn't that make sense? You wouldn't just take one person, that's not good enough, right? One person does my program and they do good on the SAT, that means shit, really. I want a nice diverse group of people to take my program, let them take the SAT, and what am I gonna compare their score to? How am I gonna evaluate their score?
Compared to the population.
Yes, compared to the population. I like it. And we do have the educational data that tells us the current, like, average SAT score, right? If we're educational researchers, we have access to that. Okay, are you guys understanding this so far? I mean, that's pretty, like, we could have said this on the first day. If I would have said, I have a program, how would you tell if my program works or it sucks? You would have people take it and see what they do. All right, pretty beautiful. So let's say we have 58 people that we randomly pick, and they go take my program, right? New marker. Damn. All right. Okay. And let's say, I should put up here that the population mean SAT score, I have no idea what it is now, but let's just pretend like it's 900. Does that sound reasonable? I'm so far removed from the SAT, I have no freaking idea. So we'll just pretend like that. I think it's on a 1600 scale. Okay, let's go with this. And let's say these 58 people, they take the SAT, and their mean, of course it's X bar, because it's a sample, their mean that they get is 911. Do we stop right there? Can I make my commercial and put it on TV and say, I've clinically proven that my program works, come take, do good, have good life? No, why not? Why is that not good enough? Isn't that higher? Isn't that better? Yes.
Because 57 people could have gotten a 0 and 1 person went.
Well, one person couldn't make up for 57 zeros, but okay, your argument is that some people could have done worse.
A lot more people could have.
But the claim is my program improves the mean SAT score, right? So I'm not necessarily talking about individuals. Okay. Or I could say like it would improve your SAT score, but that would be a whole other thing. So we're only looking at means, but I like what you're saying. There could be lots of variability in my study, but the mean still came out to be 911, which is above 900. But there's something more fundamental that's not good enough evidence. If my program didn't do a damn thing, if people would do exactly the same on the SAT, if they took my program or not, right? Could there be a group of 58 that got 911 average on the SAT? Could there be a group of people, 58 people that got 820 on the SAT? Could there be a group of 58 people that got 1020 on average SAT? Yes. This is just a sample. A sample cannot prove a damn thing by itself. Second thing, so here's the mean. And I didn't really say this up here, but SAT scores are known to be normally distributed. Roughly enough. But it doesn't really matter. I don't need to say this because I'm not graphing individuals. I'm graphing groups of 58, which of course are normally distributed because it's greater than 30, right? Okay, I like it. Can't a group of 58, couldn't they happen here? Is that impossible for them to be up there? No. In fact, if I take a sample, the variability could be whatever. So not only, I really want this to make sense, not only must our sample be greater than 900, it's got to be unusually higher than 900. That's what a sample, if a sample is in a place I would not expect a sample to be. So if this is the real picture, where would we expect samples to show up? In here, yes? In fact, we're gonna change this a little bit depending on the situation, but what is currently our understanding of unusual? Where does, yeah, 2 standard deviations up and down, right? I would expect a sample of 58 to show anywhere in there. So where would my sample have to show up to go, wait a minute, that was unexpected. That's evidence that it's higher. It'd have to show up here. We stop for a minute. Because any sample, that was like a second, sorry. Any sample that I take could show up anywhere in here and it wouldn't be unusual, right? It would not be unusual in there. Why would that show evidence for anything? That's if the mean really is 900, sample could show up anywhere in there. So what would show evidence that the mean for this group is actually more than that is if my sample was unusually high. Sounds like a whole different test, but that's okay, maybe. I really want that to make sense because we're trying to show, what we're really trying to show is that this black curve is for everybody. All groups of 58, when they take the SAT, that's what it looks like. I'm trying to show that for the people that take my program, they actually look like this, maybe. Well, we're telling you this is normal. That one is more like a toe. Oh well. I really want, you guys kind of with me? I want to show that the distribution for people that take my program is actually up. The mean is actually higher. So the only way to show evidence of that from a sample is for it to be so much higher than where I would expect it to be. So if my mean was really, so if I got a sample here, that is really unusual if the mean is there. Do you guys agree with me? Because it's way farther than 2 standard deviations away, right? What if the mean is here? Is that unusual? Now, if the mean is here, is that unusual?
No.
Shit, no. I really want that to make sense. So I can't stop just because my sample is bigger, in this case. It's got to be bigger enough. It's got to be far enough away. So it's bringing back that idea of unusual. Okay, maybe. So it's sort of like, you give aspirin to somebody, and there's a range of times that it takes to take effect. Yes? You guys with me? So if somebody's like, I made a new drug that's going to be a lot faster, it better act unusually fast for me to believe your claim, right? I don't know if you guys are, no? A little bit? All right. So if I'm you, I'm worried about these 5 steps I discussed, right? So this is the idea. This is the idea. Let's talk about the steps. So let me go back a step here. Yeah.
Is this chapter 9?
This is chapter 9. So let me ask you this. Can somebody help me? What is the claim that's being made in this problem? What's the claim that's being made? Yeah, it improves the mean SAT score, right? So my claim is that the mean SAT score should be how related to this? If you take my program, the mean SAT score for the people that do that should be greater. All right, so the claim is this. Is that cool? If I would have, so there could be a problem where we think that the cost has decreased. Okay, that's going to be less than, right? We could say, we think that the cost or that the whatever is different. That would be either less than or greater than, right? If I said, I claim that the mean is different from 900, that could be greater or less. So let me ask you this. I should have erased my earlier picture. Do you guys think this is a one-tail or a two-tailed test? Where does my sample have to show up to show evidence that that's true? Do you remember the picture we just had? Where does my sample have to show up? So here's the picture with 900. Could my sample be here? And it would show evidence for this?
No.
Nope. So it's not that tail. How about up here? Does that look more like it?
Yes.
That would, yeah. So it's a one-tail test. Holy shit. That's why that t-score chart has one tail, two tail. Right? So at the step in the test where I'm gonna go look up my Z or T, they're gonna give me alpha and I'm gonna know if it's a one-tail or a two-tail test. So I know exactly where to look. All right, so this is gonna be a one-tail test because the sample's gotta show up above. Now, if that's my claim, what am I kind of fighting against? What am I, what's the right way to say that? What would somebody who thinks that I don't know what the hell I'm doing, what would they think about my claim? What would they think? So my claim is it's greater than 900. Somebody who thinks I'm a complete dipshit, what would they think would happen after my program? Do they think I would improve their scores? So they would think the exact opposite of this, yes? Does that make sense? So, anytime a claim is made, there's inherently an opposite of that. Does that make sense? What's the time? So, there's these two kind of statements, and these are actually what we're going to call our hypotheses. This is one hypothesis, and then there's going to be another one which captures the opposite of this. Okay. You're going to love this. We'll see how you feel about this. And oh, that's right. I got to remember, this book uses, I always forget. I think this book uses, yes, okay. One thing, so we're going to use big H for hypothesis, makes sense. Big H means hypothesis. And one of the hypotheses, we're going to call it the null hypothesis, a little zero. So this is the null hypothesis. Okay, so we're going to fill that in a minute. There's going to be something that goes here. And then the other one is called the alternate hypothesis. Thankfully, this book uses HA. So going forward, these will be affectionately known as the ho and the ha, right? Okay. If you don't want to say those, you can say the null and the alternate. It's totally up to you. So here's the idea. Let me see if I can really lay this down for you. Why did I put my tail up there? Can somebody point to one quick thing that told me why it's up there?
It's greater than.
Greater than. That's all you gotta say, right? What's the opposite of this? What's the opposite of mu greater than 900? Nope. Less than or equal to 11. All right, let me ask you this. What do you guys think about this? If I thought the average age of students at Grossmont was 28, and I took a sample, and my sample mean is 28, does that prove that the mean is 28? I thought it was 28, I took a sample mean was 28. Does that mean it's 28? Does that prove it? No, you can't prove anything. You can't prove anything with a sample. So, you just gotta stay with it. Any statement that has an equal in it I can never show evidence for that with a sample, right? Just because my sample mean is equal to something, it doesn't mean anything, because the sample's got normal fluctuations in it, yes? So this statement, I cannot show evidence for it, because it has an equals in it. I can't show that it's equal in that. I can't do that. Even if my sample is exactly 900, that doesn't mean anything. But I can show evidence of greater than, like we talked about. If it's so freaking up here, that is evidence that it's not 900. I can show evidence against something. This is a lot like court cases, right? You guys get this feeling like, what are you assumed when you go into a court case? What are you supposed to be assumed until proven otherwise?
Guilty.
You're assumed innocent until proven guilty, right? So these two are like innocent and guilty. We're trying to find evidence of guilt, but can you prove somebody is innocent? Not really. You just can fail to show that they're guilty. Does that make any sense? Even if all the evidence doesn't add up to somebody doing something, does that mean they're innocent? No. We just don't know. We can't say they're guilty. You guys kind of with me? Maybe? I really want you to understand. You cannot prove innocence. So, this is always going to have the one with an equal sign. So then this will have the one without an equal sign. So when you write your claim down, you're going to put it in the right place. Does this have an equal sign? No. So I'm going to put it here. So what's going to go here? The opposite. I can show evidence for that, and you can see over there where the evidence has to be. It's got to be way the hell up there. This one I can't show evidence for. So the null always has the equal sign, and the alternate doesn't. That's it. All right. And this, our claim could have an equal or not. Okay. Let me see. Okay. Step 2. So that's step 1. Step 1 is definitely new. We never talked about hose and haws before. But it kind of is built on older stuff. Step 2 is old shit. Step 2 is, why are we allowed to do something, and what are we going to do? Right? So there's one thing missing from this setup that I need. So what if I told you we know this? Sigma is 129. Let's say we know that. Because it's the same place we got the mean. We know the standard deviation. So what am I allowed to use then? Z or T? What 2 things do I have to check? Zort. Zort? Question mark. I love you guys. I appreciate you putting up with me. Yes? So there's 2 things. We know sigma. More importantly, we have to know if it's normally distributed, and even if I didn't say this, why do we know it's normal? Okay, sample size bigger than 30. I love it. Yes. So the first step is, what the hell are you talking about? Sets up what we're trying to show and all this kind of stuff. Second step is, what are you going to use to talk about this shit? Z or T? Yeah, I like
Z.
it. Yeah, so in this case, we're going to use Z-scores. Now, can somebody, right now, where's this? We talked about this just a minute ago, but until I give you more information, what does that line mean? Do you guys remember?
2 standard deviations.
2 standard deviations, because that would be the line where what starts?
Unusual.
Unusual, right? So anything over here is fine with 900 being the mean, because that could happen easily. If the mean is 900, it could be there. But anything over here, if I get a sample that's there, that's unusual. That's unusual. So probably it's not 900. It's probably higher, right? Or something really unusual happened. So we got those two things. So how am I going to know what that is? Because it's not really ever going to be 2. It could be 1.96. Remember, that was the more precise thing. They're going to have to tell me how unlikely something needs to be to show evidence. So, so if I thought the mean age was 28 and my sample's mean age was 28.1, is that really far away? I want to see if anybody says something. I don't know the standard deviation, but I'm pretty sure that 28.1 is not far away from 28, correct? So it's definitely not going to be far enough away to show evidence. So it's definitely not going to be unlikely to get 28.1. But if I thought the mean was 28 and my sample was 47, even not knowing the standard deviation, that feels like it's pretty damn far away. That's probably pretty unlikely. So they're going to have to tell me what alpha is so that I can figure out what the z-score is. So the next step is setting up where does unusual start for this situation? Where does evidence start, right? This is not enough evidence. This is enough evidence. So it's the line between far enough away and not far enough away. That line is going to change. Why does that line change? I think earlier this semester, I might not have done this. If you're in a nuclear power plant, did I talk about this before? And you're sitting there doing your job, flipping switches and stuff, and then you see this little dial over here and the little arrows in the green, but it starts to go towards the yellow. Are you with me? It almost doesn't matter what it means. You're in a nuclear power plant. Are you going to wait for that to get like almost into the red to get up off your ass? So for you, unusual is not 2 standard deviations away. If I'm in a power plant, unusual will probably be half a standard deviation away from normal, yes? Away from the mean. Are you guys at all with me? But if I'm in a situation where I'm like, I don't know, shit, Jeff, what the hell? I can't think of a situation. Are we going to have enough pizza or not? I don't know. I don't have a good... Something where the stakes are low, right? Then I can let my unusual start further away. So depending on how bad it is to make a mistake, we're going to change where unusual is. Does that make any sense? It's really bad to make a mistake in a power plant, so I'm going to pull unusual back, right? But if we're just talking about, not having enough toppings on my pizza, I might put it out there. Okay, all right. So this third step is, they have to tell me what alpha is, so then I can set up where unusual starts. So what if I said alpha was, you could do it, Jeff. Let's say alpha is 0.025. Can you look that up for me? On the t-score chart, of course. How many tail tests is this? 1 tail test. And alpha is 0.025. So what is the z-score? 1.96. So it's our standard, it's our good old buddy here. Yay. It's the same old thing, but it doesn't have to be. The alpha could have been different. Another quick example. I think this is on, if you're trying to prove to an insurance company that your rate should go down because you installed something or other, wouldn't they make their alpha pretty small because they don't want to lower your rates? So they're going to be like, your proof has got to be damn good. I don't know, that's maybe that bad. All right. Okay. So what does that mean? That means, so let's draw that down here. Now let me just get your impression of this. All right, I always think of these as 2 old people in a coffee shop arguing where they have opposite opinions. So which old dude, or would be shown to be wrong if we got in the shaded area? Which old dude would be shown to be wrong if we got in the shaded area? Where does this old dude think it is? He thinks it's less than or equal to 900, right? He thinks it's around here. So if we did get way up here, doesn't it look like he's wrong? He thinks it's at most 900. So if we get way the shit up here, it looks like he's wrong. Can we reject what he's saying then? That's a little formal, I reject what you're saying. But that's what we say. We say if we get a sample with a z greater than 1.96, we can reach, you're going to love this. What can we reject? We can reject
Oh,
the hoe. Good. If we can reject this person, what does that mean about this person? How do we feel about this person? If we say, you're saying weird shit, what do we say to this person? Say again?
He's right.
Looks like he's right. So officially we say we support this person. So if we get in here, we can reject what this guy says because he's the guy who thinks it's around 900, and we can support the other guy because he's the one that thought it was way the shit up there. Can you stop for a minute? Step 3 of 5. Right? Okay. Sorry. All right, I don't want to lose that. Let me see, where can I go? I need more room. Oh, I guess I can take that off. All right. So step 1, what the hell are we talking about? What's the claim? What are we trying to analyze? Step 2, how are we going to analyze it? Step 3, where does evidence start? So it kind of makes sense. The next step should be, did we get enough evidence? All right. So help me out. What did we find in our sample? We got a sample mean of 911. What was our standard deviation? Oh, it's known. No, there you go, Chuck. 129. N was 58. So what's the new standard deviation? Don't I have to change my standard deviation because I'm talking about sample means I took a sample, right? It'll be the old one divided by what? Square root of 58. I like it. I like 17. I can't be more precise than that. I don't know. Damn, I'm doing pretty good today. All right, what was sorry? 16.9. 9? 0, 0?
No, 3.8.
3.8?
Yeah.
Like that? Because we all know standard deviation at least 3 places, right? So what I'm going to do right now is, where does unusual start for this problem? 1.96?
Yeah.
1.96 standard deviation is above, right? This is a z-score. So what I want to do is I want to take our sample and change it into a z-score so I can see, did it get far enough away? All right. One weird little thing I do, isn't there already a z-score up here? 1.96, right? So what I do is I call the z-score that I'm going to create for my interval, for my sample, I call it z star, just because.
Is this still the fourth step?
Still the fourth step, yes. So the fourth step is get your sample stuff together and make a z-score.
Okay.
So then you can see, did I get far enough away? Did I get enough evidence? I got too far away for you. Okay. So somebody help me out, what is that? Oh man, I don't want to do it anymore. I'm tired. 111, 1711, so 9. 1.53. I'm probably really off. At some point my bucket's got to run out.
0.64.
What is it?
0.6494.
0.64? I'm really off. What did I do? 6.5? Alright, so I knew my luck would run out. I don't know what I just did. Oh, I know what it is. Anyway. Is that what everybody else is getting? Yeah. Is that, did we make it very far from where the mean is supposed to be? We only made it less than a step up. So can we reject the null then? Can we say he looks wrong? Do we make it far enough away to say that he looks wrong? Where did we have to make it in order to say he looks wrong? If we get a sample with a z greater than 1.96, we could say he's wrong. So did we make it far enough away to say he's wrong? No. We fail to reject the ho. Fail to support the ha. Alright, and then there's one more step, but let me do this. Let me give you, this is going to be like your go-to thing. It's got every step explained in a couple different ways. Right? So let me just give this to you. Let's see. What? Okay. So read through that real quick. Man. And I am, well, this, I made this about 10 years ago by now, I think. So who knows why I was thinking about northern Minnesota coyotes. I don't know if they were the news or something. Do you guys get the basic gist? Does it kind of make sense that animals might live longer if they're given more room to move around? Aren't there many animals like that, especially elephants and stuff, right? Intelligent animals. Yeah, so he takes a sample, and sure enough, it's 12.45 years. The sample mean is 12.45. That is bigger than 10.15, but like we already talked about, that's not good enough on its own. So let's do this. Let's do this. I don't think you guys will mind if we stop now. I'm just really tired. But next time we'll kind of go through this. And I've got, trust me, I don't know, we're going to be doing quite a few of these over the next few classes, right? Just to get it used to it. And then we've got to do hypothesis test for percentages, right? So this is a hypothesis test for means. We're going to have a hypothesis test for percentages. So on this paper, by the way, I've got stuff written in black and stuff written in red. And to be honest, I can't remember. There are like two different ways to explain something. I think the black is more technical and the red is more of a general idea. Yeah.
Real quick, what are we doing for step 5?
Oh, step 5 is going to be the conclusion. Step 5 will be the conclusion. So, real quick, what was the claim? Which one of these was the claim?
The alternate.
The alternate was, right? And so what could we do with the ha? Couldn't we support it or fail to support it? That's what we could do. Did we support it? Did we get far enough away? No, we failed. So we have not found sufficient evidence to support the claim that this program increases SAT. Isn't this the same thing? Yes. Increases SAT scores. So after I do this hypothesis test, I'm shown to be a fraud. I don't make my commercial. You guys with me? Okay. And now if I really believe in my program, I might take another sample, I might try again, because just because it didn't work once, it could have just been a bad sample, right? So you keep trying. But we'll do more of that. Yes?
For number 4, are we gonna write anything else, or are we just gonna leave it like that?
Yeah, right here you should put, right here I could put fail to reject the null, fail to support the ha. And when we do some more examples, people always have trouble remembering how to write this. And the key thing is, my claim was the ha, so I'm gonna use this language, not that language. Because I want to talk about the claim. Yeah.
And so like on a quiz or a test, like all those steps of 1, 2,
I do,
3,
yeah, I do A, B, C, D, I, yeah.
So it'll be all these
It'd be
steps?
that, just with less, obviously,
Okay.
explanation, yeah.
Alright.
It basically would be those 5 steps.
So the z-score would have to equal, in this case, more than 1.96?
Yes.
Okay.
So if we would have gotten Z star to be 2.07 or something, we would have said, we have found sufficient evidence to support the claim. And then I could have made my commercial, and I could have said, it's been clinically proven to improve your, this is what clinically proven, well, this is one thing that clinically proven might be, is it's gone through this process.
This is just a way to interpret the data. It's not really anything like new.
No, it isn't.
I don't wanna say it's not anything new.
It isn't. It
It's
really
like the
isn't. It
same-
truly isn't anything really new, but it's new in the sense that we're putting a lot of stuff together that we've never put together. Sort of like the automobile. Glass existed, tires existed, but then they put it in together and it was a freaking car. It's like, holy shit. No, you don't like, okay. I always like that example. Before there's a car, we had all the car parts. We just didn't know to put it all together. All right, guys. Have a good weekend. Have a good Halloween.